Ok, estamos ao vivo. Espera para colocar isso. Entra que faço coisas aqui. Hello. Olá, Glaston.
Olá.
Olá.
Me ajeitando aqui, foi mal.
Está enviando o link do YouTube.
Assim que você entra no Zoom, já tem como criar um link no YouTube, então?
Sim. Deve entrar, cada vez muda esse problema.
Entendi. Uhum. Porque no evento das mulheres na matemática na FRJ, eu ficava esperando, eu entrava no canal e ficava esperando, mas aparecia tipo 2 minutos antes, ou talvez até um pouquinho depois do tempo.
Não sei, deve ter uma maneira mais sofisticada de fazer isso.
Bem possível, bem possível.
Será que vou enviar novamente o link para o Ángel?
Sim.
Vai que esqueceu. Hello. So, since we are few here, Erica and Georgia. Georgia is from Spain. Oh, hi. Erica is from where? So.
Italy.
Ah, italiana. Ah, piacere.
Esatto.
Di quale città? Quale città?
Come università o come...
Come i due. Ah, Padova. Ah, sì.
Io sono nata a Venezia, vicino a Venezia, in provincia.
Ah, sì, mio papà era di vicino là e mia nonna viveva a Arcella, quindi sì. Ah, Georgia is from Greece. Hi, Georgia. You want to say hello? So, Georgia? No, you can speak maybe. So, Erika, lavori in meccanica celeste? Stai facendo...
Astrodinamica.
Astrodinamica, quindi proprio perfetto. Stiamo cercando di navigare e toccare un po' vari assunti, visto che internet ci permette di viaggiare senza costi.
Giustamente,
no?
non sfruttare.
Esattamente.
Sfruttiamo perlomeno l'unica cosa.
Olá, Carlos.
Como estão?
Estamos bem. Let's speak in English. We were speaking in Italian.
Ciao, professora.
Pedro. So I'm getting confused. Which language? So
English, Stefanella. English. Remember.
Yes. So Erica, Glaston also is working in astrodynamics.
Yes, I was Angel's student.
Okay.
Yeah. Now I'm working in Poland.
Okay.
Yeah. So, and 1 second.
Angel.
Sì.
Ara parlem una mica de català. I'm sorry.
I understand now. After my 2 months course, I understand better, but it was not enough. But it was a miracle. I started understanding Catalan.
It's not a miracle.
No, but you have to study.
Every Romance language is an interpolation of the others. So if you know Portuguese, Catalan, and French, you can understand Spanish. If you know Spanish, Italian, and French, you can know Catalan.
Yes, I know, but a minimum time, I just took 1.5 months of Catalan. So. Alessandro.
Ciao.
Aspetta.
Speaking of Italian, we are Italian, Stefanella and I.
Sì, sì, no, ma c'è un'altra italiana. There is another Italian.
Io capisco un po' di italiano.
Sì.
So your mother language is Catalan?
No, it's Portuguese.
Portuguese, okay.
Yeah, but I do speak Portuguese, Spanish, and Catalan since I lived 3.5 years in Barcelona.
Okay.
But, well, I visited Italy several times. I can somehow make sense of it.
But I've heard that a Portuguese speaker can understand Spanish, but Spanish speaker don't understand Portuguese. So.
That's true.
Yeah.
So I have actually I don't know. Well, Stefanella knows a former colleague of mine, and now she moved to Rio, and she is Romanian. And my impression that Romanian understand everything.
Yes, exactly. Yes.
Like Italian, you know.
Yes.
Spanish, yes. like, and at least I don't understand that. You know,
no, Romania is very difficult.
Yeah,
and so we have another Italian since there is Maria Annunziata, no?
Yes, I'm Italian.
Martina.
Martina.
Yes,
sorry,
Martina.
Sorry.
Don't worry.
So you are from Salerno, University of Salerno?
Yeah, University of Salerno, yeah.
Ah, so is there a group of celestial mechanics, astrodynamics? What kind of dynamical system over there?
Continuum mechanics.
Okay.
I confess that I didn't come to Salerno. I went to the other side, Lecce, for a school.
There is also
yes, in Puglia.
There is also a person from Padova, actually. Erica, are you from Padova?
Yes.
I studied in Padova many years ago. Okay. You know, I was a student, like more than 28 years ago. So, yeah, a long time ago. Now I live in the United States, but yeah.
And Alessandro, so what kind of dynamical system in Toledo?
Well, actually, we have a person that I collaborate with. We do bifurcation theory. I-dimension bifurcations mainly apply to biological problems. And then with some other people, actually in Italy, I deal with integrable systems mainly. So I got interested in symplectic geometry, and I taught a class essentially in symplectic geometry. And with my new PhD student, who's actually from Turkey, he should be here. We are so there is a new book. I mean, I think it came out in 2019 or 2018 about the use of symplectic topology in celestial mechanics, specifically three-body problems. So,
very interesting. So if you can send me the I'm fan of topology, so I will send you our article.
No, there is also,
we just a little bit exploring. We started.
No, but you know why? Since I know you worked on vortices, right?
Yeah, but even gravitational, yeah, we start playing.
No, but vortices, point vortices in ideal fluids, right?
Yeah.
And I think one can actually use some of the techniques to explore vortices dynamics for small number of vortices, but
No, there is a lot of fun stuff. Definitely, we should talk, and we just begin, because we can formulate in a variety of geometries, so there is a lot to do. Angel is here, so you can I already habilitate you, Angel.
Should I share the screen?
Let's wait 1 second. If someone else, just to get to know each other. There is someone else from they would like to talk about their research group or where they're from. Someone. Let's say George Gonzalez. Let's see. Well, Glaston, since you can talk about what's happening in Poland. Well.
Lockdown? No, I'm lying. Sorry. No, but people from here are more from the computer-assisted proofs side. So I'm the weird one here. I'm the only one who do not do computer-assisted proofs yet. I hope in the near future, but.
Well, you know, eventually you will learn new stuff,
Indeed.
new horizon. When one moves from PhD, is always the weird one when it goes to a new family, for definition. For definition. Okay, I think the people are still arriving. Maisa coming back.
Hey, Gladstone.
Hey, Banu. Long time no see.
Yeah, long time no see. I can see one thing you have not been doing is cutting your hair.
No, not the hair, nor the beard.
Yeah.
I was looking like you until about 2 weeks ago.
It was intentional. It was intentional.
Yeah, in my case, it was no haircut due to the virus, of course, until I got vaccinated.
Well, the hair is a long story, so it's long before the virus.
Yeah, that's true. Your hair's always been long. I guess it's your beard more that's big now.
Yeah. No. When last time we met, I think it wasn't that long.
No, it wasn't.
Yeah. Quarantine.
And Maisa, how is it going over there?
Hello, everybody.
Hello.
I'm fine.
So you're very much locked down? How is it?
Yes, totally at home, living just for buying food, buying drugs, medicine.
Yeah, you're lucky. I just have water delivered because there is no way I can carry 20 liters of water. And the last person that delivered water, he looked around, and next thing I know that someone tried to break in my apartment. I was not here. Yes, fortunately didn't succeed. Yes. Imagine nowadays if someone steals your computer, you know, like we are.
My God, no.
It's like death, you know. So it's special. It's not easy. Otherwise, how is it going there with research? With how the students, the group you meet online? How's it working?
Yes, we have to work at online, but it's more complicated to work online, you know. It's not as face-to-face.
Yeah. Now with the students, it's very difficult. With the with not research students, with the usual students.
Yeah. And we have to prepare all the classes and slides and make movies.
Yeah, you can be spontaneous, you know, it's just the spontaneous interaction. And the students are very much inhibited to talk in the and you can't really impose on them. Some of them have serious psychological problems, so you can't impose on showing their face.
Yes.
It's getting complicated. We have more, it's not easy time. Let's hope we get presential, but at least we can enjoy this. So I think that, people are still coming, but, Renata, how is Germany? Renata, I don't know, can you speak? Maybe. Hi, now she can speak. So we have even someone from Germany today. Germany is good. Okay. Okay, so I think you can share the screen and I will remember to record. I don't have to forget to record. 1 second. No breakthroughs. 1 second to record. Okay. So great pleasure to have the second lecture of Evangelic Jorba from Barcelona, speaking to us about a little bit more about astrodynamics today, if I'm not wrong. Angel, please.
Yes, I mean, yesterday somebody told me that some of the slides were not clearly seen, so I've changed a few things. So I hope now it will be clear. So if you can you see it, my screen? Well, my slides with my mouse.
Yes. 1 second. There is an interference. Is it possible that it's your telephone next to? Sometimes Zoom has some weird intersection. If there is there are too many microphones. Only one computer with the audio and the other not. This is yes, Angel?
Yes.
Okay, so go ahead.
Okay, so let me start. Today I will focus on, on a different kind of manifolds that the ones I discussed yesterday. So I will discuss the usual stable and unstable manifolds and the potential applications or the applications for controlling things. So let me start, simply to make the most basic definitions. So I think everybody is familiar with this. So imagine we have a two-dimensional matrix, two-dimensional linear system, a differential equation. Everything is real, so we can draw. And in this case, we assume that the matrix A has two eigenvalues, which are real, one positive and one negative. So if B1 and B2 are the corresponding eigenvectors, then we know that the phase space of this system is something like that. So everybody is familiar with this. And here it's also trivial to define what the stable and unstable manifolds are. So they are straight lines going through the origin. The origin is an hyperbolic fixed point or equilibrium point. So, and then if we take the two lines using V1 and V2 as the direction vectors, we get the invariant matrix. Okay, that's very easy to do, very easy to define. So the question is what happens when we add nonlinear terms to the plot. So as you can guess, things get deformed. So let me make a second drawing. That's also a drawing you have seen. Now, for a moment, let's focus on the hyperbolic point, which is this, right? So, well, so at first sight, if we are very close to the point, we see the same plot as before, the stable and unstable manifolds. But if we enlarge our view, we see that the manifolds are not straight lines, but they bend. So I have to define them in a different way. They are not lines, they are curves. So I have to find a geometrical definition for them. And that's the first step. So usually, there are several ways, but the standard one is this one. So if we have a smooth, as usual, everything will be smooth. So if you want analytic, but as differentiable as I need. Okay, no linear system. Now let's jump to n dimensions. And then I have a equilibrium point that I can select at the origin. That's not a restriction at all. I can always do that. And then let's define first what I call the stable set. What is the stable set of zero? It's the set of points such that the orbit at the start at these points goes to zero when the time goes to infinity. Okay, that's very clear. So for the unstable, we have to do it the same thing, but backwards in time. Unstable means you are going away. So, but as I have to define from the point, I have to choose that the time goes backwards in time. So the unstable set is a set of points such the orbit starting at those points goes to the origin when the time goes backwards to minus infinity. Okay. So with this definition, we still, that's very nice. So our previous example, it can be applied and we get the same lines. Those lines verify it. But the thing is that with this definition, we get rid of the necessity of talking about the straight lines or whatever. So it's a dynamical definition. So we define the manifold from the point. So, well, note that these sets can be empty. So I don't need, for instance, in these points in the middle, So the set of points that in the future, times going to infinity or backwards in time, they tend to 0, the set of points that do that is empty. Well, it's besides the point itself, okay? So it is trivially there. So, well, not everybody's, I mean, these manifolds can exist or not. You need some situation like hyperbolicity, you can guess. I mean, with this condition here, you don't have them. So, well, as our applications will be in celestial mechanics, so it means usually it's a Hamiltonian or close to a Hamiltonian, in the sense that in some situation in astrodynamics, you have a non-Hamiltonian perturbation of a Hamiltonian system, so you are not in a Hamiltonian setting any longer, but you're close to it. So I mean, this sentence is cut. I'll have to fix the slide. Okay, so what is missing is that because of that, I will assume that the hyperbolic things are saddles. And that's typical in Hamiltonian and systems close to Hamiltonian. Okay, so, well, so the first thing in the generic conditions, now next I will give a theorem, it is possible to show that these invariant sets, I call them sets, I didn't say manifolds, because in principle, with my definition, I cannot say they are manifolds. They are sets that give rise to orbits going to the point, either forward or backwards in time. But under quite generic conditions, you can prove that they are, in fact, smooth manifolds. Okay? So in principle, let's start, another typo here, let's start with the case of hyperbolic points. So I mean, an hyperbolic point is a point completely hyperbolic. So if I linearize the dynamics of the point, I have no center direction. So the eigenvalues are either positive, real, all eigenvalues are real, and they are either positive or negative, okay? So, well, let's denote by ES, the stable linear space, or the delinearization at the origin, and EU, the unstable linear space. Well, as usual, I assume that the hyperbolic point is located at the origin, so that's not restriction at all. And, well, I need to refer to the dimensions of this space. So let me call M the dimension of the stable space. So it means the unstable is N minus M, okay? So, well, there's this theorem. Okay, well, this is a very classical theorem. I would say it's very well known. So, if I have a vector field, differential equation, 0 is an hyperbolic at this point, and then I don't need anything, essentially. I don't need to add any condition that the vector field is smooth and that 0 is an hyperbolic equilibrium point in the sense I've just defined. Okay? Only with this, I can tell you that there exists an m-dimensional manifold, WS, and an n minus m-dimensional manifold, U, that would be the unstable. The hyperbolic point belongs to both of them, such that all these four conditions are met. So first, the manifolds are invariant. I mean, this is a local invariant in the sense that this is a local theorem that happens in a neighborhood of the equilibrium point. So the second is that they are tangent to the linear spaces. So the stable manifold is tangent to the linear stable manifold at the point. The same for the unstable one. Oh, sorry. And the definition we gave before of invariant set of a stable and unstable set is met. So if a point belongs to this manifold, the stable one, then the orbit goes to the point when the time goes forward, and it belongs to the unstable, the orbit goes to the point when the time goes backward in time. These manifolds are, well, locally, this is a local theorem, unique, and they are the only ones satisfying these conditions. Okay, that's a standard theorem for invariant manifolds. Well, there are plenty of situations besides this one, and there are plenty of theorems, and you can play with the conditions. I mean, well, this is quite usual in dynamics. So I mean, if you Google it, you'll find hundreds of theorems for different situations, even for parabolic points. Oh. So what I will do today is I will work only with the linear approximation. So and you'll see why. I mean, in next week I will use high order. I mean, I use the manifold far away, so it won't be linear anymore. But I mean, as this is the first part, I will focus on the linear part. I will not survey all the theorems. At the end, I'll give you some references so you can go and find theorems for other situations. And in the next week, I won't prove the theorems, but I'll explain the hypotheses, why they are needed, where they are needed, because they appear in the computation. So this will allow me to discuss a bit the theoretical part. Okay, so I'll do, let's say, one application, or the two examples, is to control a spacecraft near an unstable equilibrium point. Okay, so in principle, I'll choose a saddle center point because it's plenty of them in astrodynamics, the restricted three-body problem, and in perturbation restricted three-body problem. I choose a point. I could do the same for a periodic orbit, but I choose a point in order to explain easily all the ideas, and everything can be also readily transported to periodic orbits. So I mean, once you understand why we do why or how we are doing it, you'll see it's pretty clear. So we assume we are close to the point. So let me do the first trick. So linear approximation, let me tell you, is good enough. Okay. So you can complain and saying, how do you know it's good enough? You are cheating, blah, blah. So, but of course, this includes an error in everything. And I'll discuss that at the end. Okay. So I for the moment, I mean, I have to start at some point. So let me start assuming that we are close enough to the point such that the linear approximations is going to be good for what we are going to do. Okay, so we are in a 6-dimensional phase space, saddle center. And let's see how we can visualize the dynamics near the point. So a standard trick to visualize the point is to choose suitable coordinate planes. So I'll choose the one plane will be the saddle plane, and the other two planes will be the planes of the two centers. Okay, so if I start a trajectory near the point, the dynamics is very easily described like this. So that's the saddle behavior and the center behavior. Okay, well, imagine this point is L1, L2, L3, any other situation, any other point. They all belong to this category. So we want to keep something there. So for the moment, let me assume the model is exact. So we could discuss also, I mean, how good is this model for real problems, but not now. So let's assume the model is exact. But of course, we don't put the spacecraft exactly at the point with 0 error. We make some little error when we put it there. So because of that error, in that plane, I'm moving away. These two planes, I don't care much because I'm simply moving around. So distance not increases, but that one increases. So this means that I have to do something. Otherwise, the probe will be sent away. So I have to do something. So, well, several options. One option is to use control theory. This is, I won't do that. I mean, control theory means to define some objective function that you want to optimize that has to do with the distance to the point and the fuel used, blah, blah. And then looking for a control. That controls appear as a parameter in the differential equation because they correspond to giving some impulse or doing something. And then you try to solve that by optimization techniques. So I won't do it. So I will use the manifolds. Okay, and I will use them in a linear way. I mean, I can do the same talk, explain the same thing using nonlinear manifolds, but that would be a bit more complex. But it's the same idea. So let me focus on the linear case. Okay, so, well, here dynamics is very clear. So as we understand dynamics, let's try to use this knowledge to derive a suitable control strategy. Okay, first, I have to explain what is a maneuver. So what can I do with a spacecraft? Well, it depends on the kind of propulsion the satellite is using. So today I will use two kinds of propulsion. This is the first. I mean, in the first block, I talk about the first kind of propulsion, which is the standard one, the chemical thruster, the rocket. Okay, so this is based on burning some chemicals such that you produce thrust by ejecting high-speed gases. Okay, so and then I mean action-reaction principle. is giving you a push when you do that. So it's the simplest way. So, well, I mean, if you compare, I mean, that's a comment simply to explain that, well, these types of engines, as the classical ones, they are, as a good thing, they are the lightest and they have the highest thrust, I mean, the highest push, but they are the least efficient of them. Okay, so that would be another discussion. I mean, if you have curiosity, ask me at the end and I'll explain why this happens. But they are, I mean, they have been used a lot. So I'll use that as a first option, okay? Well, I mean, a chemical thruster gives a big push on a short time. I mean, I think that a chemical thruster, once you have ejected all the mass you are carrying to be burned, your engine is over. You cannot do anything else because, I mean, it's action-reaction thing. So when you end up throwing away mass in order to be pushed, it's over. So, well, so they only act for short times. You only give some pushes, short pushes. And because they arc for a minute, for instance, I mean, 30 seconds, 1 minute in our units. So a good model for the action of a thruster is that simply say that your spacecraft or your satellite has experimented a jump in its velocities. Because, I mean, the amount of space you move during the push is very short compared with the jump in velocities you get because the thrust is quite powerful. Okay, so we will think of a maneuver as a jump in phase space. This jump will only affect velocities, not positions. So this means that to control, that's what I can do. I can change my velocity, but not my position. Of course, there's a limit. I mean, that's you cannot do an infinite jump, of course, that there's a limit, there's a range. But then the key point is this blue sentence, which is the following. So we have a saddle plane and 2 center planes. Every plane is 2D, that's the 6 dimensions. Velocities is a 3D plane, and positions a 3D plane again. So assume they are in general position. So they are not parallel to each other, so it's a general position. Then this means that the jump takes place in a given direction, 1D, in every of these 3 planes. So I will focus on the saddle. So I will repeat it only for the saddle. This is only true for the centers, but for them, I don't care at this point for the center. So let me focus on the saddle, okay? Because the saddle is 2D and the velocity is a space, is 3D. So this gives me a line, a direction. I think that's clear. Okay. Let me make a graphical discussion of this. So that's the saddle. Those are the 2, I mean, this is the coordinates of the saddle, nothing. So if the direction I'm discussing, let me assume is, I'll take this. Oh, so sorry. You see my mouth, right? I'm using this straight line. Imagine this is the direction. So this means I can do a maneuver and jump in that direction. From any point I am, I can move in that direction. Okay? I cannot move in that plane. I cannot jump to any place because I can only change 3 coordinates, 3 velocities, and I'm in 6 dimensions. That's the key of the trick. You want me to talk more about that or clear?
So 1 second. So you're saying that you are on the upper and you have control to jump on the lower. Is this?
Yeah. So let me make an example. For instance, imagine this is my the orbit of my spacecraft, right? So that as the time goes by, I'm moving away, and I arrive here. Yeah.
Yeah.
At some point, I decided I'm too far away. I have to react. I have to do something. So then I do a maneuver in a suitable direction such that I jump I move myself to this place.
Yes. Yes.
And then I'm happy with the result. Yeah. Because the dynamics will bring me back. Yeah.
Yes.
So essentially this plane is neither positions nor velocities, okay? So this plane, this is what I was saying, that these are in general positions. This plane is the saddle plane that mixes positions and velocities, right? So let me go here, sorry. Okay, I have a saddle which is 2D and to center which is 2D, that makes the 6. And velocities are 3D. So if they are in general position, which in fact happens in the recessive body problem and in all these problems, it always happens, they are in general position. So they are not parallel. Yeah. So because of that, it means that when you change your velocity, in fact, you are moving on a line on the saddle plane. So in other words, if this thing were inside the velocity plane, then I could jump anywhere.
Yes.
Yeah, but that I cannot do. That's the idea of controlling. So let me, I'll repeat with a different, with a solar sail in a moment. So I'll do it twice. In a solar sail, there's different because you don't have this big push that you have with the rocket. So, but it's the same kind of idea, right? So essentially the idea is that, let me go here. The idea is that when you change your 3 velocities, if you are looking at your positions here, when you have changes velocities, you have changed your positions in the 3 planes, okay? If you are here when you change velocities, you go to a different place. If you are here, you go to a different place, and you are here, you go to a different place. Yeah? Is that correct? So the key point is choosing your jumping velocity, so your direction for the maneuver, such that, of course, you don't want to go, I don't know, down there. That's really too bad. You want to find this line, the stable manifold. Okay? I mean, usually targeting to a point is more difficult than targeting to a manifold. A manifold is bigger, so it's easy to target. Yeah, so if I can move in a direction, as I was saying before, and if I'm here, I can target the manifold. I cannot target the point. And that's very easy to imagine. I mean, imagine you have an unstable point, like, so let me, probably most of you have played with an inverted pendulum, right? This kind of toy when you are a kid that you want to keep upside, so you move your hand such that you keep controlling it up, right? So in principle, the idea is that when you kick, if you want to do it with a kick, these are jumping velocities, when you kick it, in principle, you can change the velocity of the inverted pendulum, that's what you do when you kick it, but you don't change the position. So if you visualize the pendulum, the phase space of the pendulum, so I had one plotted for this thing. Yeah. So you want to arrive here, but you are moving away. When you kick and you change velocities, I mean, here velocity is in the vertical line, the horizontal is positions. When you kick, it means that you can choose in which place you want your pendulum to be, because you kick and you change velocity. Okay, you cannot change the position because it's a kick. So if you are, let's say, here and you are going away, you have to give a kick such that your new velocity is that velocity. And then automatically the pendulum goes up and turns to the point. It's better or worse?
No, it's okay.
It's okay. So it's essentially, I mean, the idea, and that idea, I'll use it also next week for transport and things like that, is that the manifolds organize the dynamics. So they organize local dynamics around a point, as I'm discussing here on the other example, and they organize transport between different regions. So you can take advantage of them. So usually, if you want to go somewhere, in the example here, if you are here and you want to go back to the point, you can point to the point. You can try to do a maneuver to go straight. But it is usually more difficult than to look for the manifold, because the manifold is much bigger than the point. It has more dimensions. So probably there are zones of the manifolds which are closer to you. So you can, instead of going to the point that's your final destination, you go to the manifold and the dynamics will carry you to your final destination. So that's the idea. It's very simple. It's really very simple. Okay. So it's to understand how manifolds organize the dynamics, and then to use this knowledge to design maneuvers or things taking advantage of that knowledge. So in that case, for instance, let me discuss again this pendulum. If I'm in this place, I'm going away, but I want to stay up. That's the upper equilibrium. I want to stay. Okay. I can use a control algorithm to go back. That's possible. I mean, and there is optimization, and then there are lots of things, and it works. I'm not claiming it doesn't. It works. But there's another point of view, that's the one I'm explaining, is that if you understand why you are going away and how is the dynamics around, you see what you have to do. You realize you're in the wrong place of phase space. You have a wrong velocity. You need another velocity, because then the phase space will play in your favor. So you kick your...
Angel, there is a question in the chat.
I don't see it.
I can read to you if you want.
Yeah.
In the full 6D-dimensional system, are you trying to target the 4 center manifold of the equilibrium, thus trying to get onto the 5th dimensional center stable manifold? Or are you targeting the equilibrium point itself, so only trying to get to the 1 dimensional stable manifold?
I'm targeting the stable manifold. That's the only thing I'm doing. I'm at this point of the discussion, I'm ignoring the center directions. Yeah. So you can complain of that thing I'm doing, and in a moment I will discuss what happens with the center directions. Okay. But first I want to explain that, I mean, this thing, I mean, as the important objects in the spacecraft going away are the stable and unstable manifolds, I can, let's say, control them if I'm able to change velocities. This has a side effect on the center directions. But at the moment I'm not discussing, I'll do it in a moment. Yeah. Okay. I think I have answered. I'm not sure.
Yes, for me, yes.
I have a question.
Go ahead.
Certainly, you have an error. You won't go exactly to the stable manifold. So
sorry. I kick something. Yeah. I was trying to see the chat and I kick. Is now back?
Yes.
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 Yes. My question is, certainly you will have an error to go to the stable manifold. What happens? You have to correct and try many steps in order to go to the stable manifolds. And what happens if you get far from the in the position space?
I mean, if you go far away,
yes,
then you need a nonlinear approximation to the manifold. You're gonna still play the same game. I mean, this game, I don't need to be close. In fact, I'm asking to be close because I'm using straight lines. I mean, I'm using linear approximation to the manifold, so I need to be close.
Yeah.
Okay, but I mean, if these manifolds bend, and I know them, I could do the same. I can apply the same ideas. In fact, I mean, next week I will use manifolds far away from the origin, which are bended, do transport, and then I will use this. Another thing is that, and that's true for a spacecraft dynamics, when you want to stay to a point, it means you don't want to go far away, you want to stay. So usually you don't wait too much before doing the maneuver.
Yes, yes, okay.
Yeah, okay. So that's that I have explained. Here I have some reference about this. Now let me go to the second example, which is a solar sail. So solar sail is a, well, here I have a picture of one. So it's a small spacecraft that has a big sail, which is a very light surface that reflects light. So when you reflect light, the light has momentum, so you get a little push from reflecting the light. And that's your propulsion. So that's a very, very small force, very, very small. But on the other hand, it acts continuously and is free. So you don't have to carry fuel or something. So it has some interest for some kind of missions. So you cannot do exactly the same that you do with a rocket. So that's a different thing, and it has a different purpose. Okay, so this is not science fiction. So several solar sails have been in space. Here I'm listing them. And they are all experimental. So, they are in a space only to play with them, see how they work. So there's no mission accomplished with a solar sail, as far as I know today. Okay. So, well, I will skip that, so you will have the slides. So first, I'll do a very simple model because this model can be improved, but I won't do it. It's simply I want to explain the main ideas of how it works. So I will assume that the sail is perfectly flat. That's not exactly true, and it's perfectly reflecting. So that's not true either. Okay, but well, let's do it. So essentially, a sail depends on several parameters. The orientation is 2 parameters. We are in the space, 3 dimensions, and the orientation of a flat surface is given by 2 angles. You can take them in different ways, they have different origins, but it's 2 angles. It's like a point in the sphere orientation. And then is the side lightness number, which is essentially the push you get from the sail. That's the other. So this has to do with the size of the sail and with the total mass of everything. Okay, so and that gives you. So essentially, this is sort of, let me call this the acceleration. It's not acceleration exactly, but it has to do with the acceleration you get from the sail. Okay, so well, there's some definitions. So if you want to imagine what a solar sail is, to get a reasonable push, which is this thing, if the sail weighs 100 kilos, then you see how big the sail has to be. Okay, that's a difficult engineering problem. This is a book about solar sails, so it's at the end, so you can. So dynamical model, let me use the simplest one, is the restricted three-body problem. The primaries are Sun and Earth, but with an extra force, which is I will assume that my particle is not only attracted by Earth and Sun, but it gets a push that is given by the Sun, by So if you write the equations, that's a bit now it's irrelevant. So this first block up to here, this is the restricted three-body problem, and this term that starts with beta is the push you get from the sail. N is a normal vector to the sail that is given blah blah. It's easy. But it's a bit boring to do the math, but it's easy. Okay. So in principle, before putting the sail, the RTVP had 5 equilibrium points. If the sail is small, well, we are perturbing. This is an example of non-Hamiltonian perturbation. In general, the effect of the sail is non-Hamiltonian. For some orientations, it is Hamiltonian, but some other it is not. So, well, the points are displaced. according to the orientation of the sail, the beta, blah, blah. So let me go straight to the application so you see what we will do. So one of the most important, I mean, and this is one of the purposes for the solar sail, is to observe the sun. I mean, having an accurate and continuous observation of the sun is very good we want to know in advance if a big geomagnetic storm is coming from the sun, because it affects our communications. So from time to time that happens, it even appears in the newspaper that there's a big geomagnetic storm in the sun. So there is a lot of charged particles that are, I mean, they don't travel at the light speed. They travel, I mean, it is charged particles with mass, so they travel from the sun to us. And when they arrive to the Earth, they interfere with satellite communications, and that's something that we want to know in advance. Yeah. So, I mean, usually now we have some satellites near L1 doing this observation. Okay, they are in a halo orbit. I commented a bit about halo orbits, I mean, on Tuesday. But a solar sail gives you another option. A solar sail means that if the solar sail is moved a bit sideways, the equilibrium point, so where all the forces compensate, moves away from the Earth-Sun line, and it's in one side. Yeah. Also, because of the gravity of the sun is somehow diminished, I mean reduced, because the sail is attracted by the sun, but it's also pushed away by the photons from the sun. The equilibrium point is displaced towards the sun. So the equilibrium point, L1, moves outside the Earth-Sun line, and it goes to one side. And that's fantastic for two reasons. One, I'm closer to the sun. That's always better if you want to do observations. I mean, and the second is that because I'm outside from this line, it means that when from the Earth I look to the sail, I'm not looking at the solar disk. If this were on the line, I could not get communications, because if I had a parabolic antenna pointing to the sail, which lies in the middle of the solar disk, I will only get the noise coming from the sun and nothing else, because that's much stronger than the emitter in the sail. So in this way, the sail is not orbiting, is fixed. This is an equilibrium point. The sail is static at one side of the sun. Okay. It can also be used to study the north, I mean the poles. So you can hover like an helicopter, but at some distance on the poles and have a continuous monitoring. But that's more difficult. That's not the, let's say, a star application. That's the star application. Okay. Now, another one that's appealing is if we want to go to Mars, because I mean, you know that is becoming more and more fashionable to go to Mars. So there's one problem, that is that because our periods are different, Earth and Mars, from time to time, we get in opposite sides of the sun. So this means that you cannot, I mean, communications are lost. You cannot communicate. So one option to keep continuous communication is using this idea to put a solar sail over the Earth, so such that the solar radiation pressure compensates for the gravity of the Earth. So you have an equilibrium point up here. So you have a continuous vision of Mars. So you can put a relay of communications and keep it. That's the okay. So same as before. Let's use dynamical system tools. Okay. So I will focus on one of these equilibrium for the solar sail, and I'm going to discuss the controlling. Now it will be a difference. I mean, there's no jump in velocities. I don't have big pushes. And yeah. Well. So in principle, now I will go a bit faster, but as I have explained the ideas and I hope clearly, now I can go faster. We are in 3 dimensions, 3 positions, 3 velocities, 3 degrees of freedoms, and these points are center, saddles, center, sorry. So the dynamics near the point is the one I discussed before. But here I cannot jump because my push is very small. Okay, so what can I do? Well, the trick here is that is the following. So I can move the sail. That's the only thing I can do. That's my only possible maneuver, is change the orientation of the sail. That's the only option I have. And what's the effect of moving the sail in phase space? if I move the orientation of the sails, what happens in phase space is that the equilibrium point moves from one point to another. Okay, the equilibrium point is produced by the cancellation of gravitation of Sun, Earth, and the solar radiation pressure. So if I change the orientation of the sail, I'm changing the radiation pressure on the sail, so that the place where all these forces cancel changes. Okay, so I can do that. I can change. That's a fantastic trick. So, well, imagine that's the point. So I'm looking at the saddle. Later I'll look at the centers. I promise that. So I'm looking at the saddle. So that's the saddle, and that's, well, I started, the sail arrives there, and it starts moving away because of the situation. Okay, so the point is that I can change the orientation of the sail and move these points to different places. And immediately you realize that that's a nice idea. Yeah, that's fantastic. If I can change the orientation of my sail and I can move the saddle from here to there, the natural dynamics will send the sail back to this. Now this is not the manifold because this is the manifold. But once I'm arriving here, I can restart the previous orientation of the sail, and that's it, okay? So, of course, I have to do it right. I mean, if, not any maneuver is acceptable. I can do it wrong. I mean, that's an example of a wrong maneuver, okay? So, well, now that this is, I think it's clear, let me go to the center. We have to pay some care with the centers. This also applies before, but I mean, I skip it to discuss it only here because, well, I only want to do it in one place. Well, if I move the fixed point, I also change where the center is. I move it. So, okay, that looks good. But if you start thinking about it, it is possible to choose the rotations in a bad way such that you are spiraling out. Okay, so you have to be a bit careful with that. The point is that, I mean, that's very easy. I mean, if you give little rotations for different centers and you can change the center, you can organize this such that you spiral away. So that's what you want, that's what you don't want. Okay, so, well, we have to choose the orientation of the sail such that the saddle behaves the way we want and the centers are not that bad as the worst case. So, well, if we think a bit, the condition to have a well-behaved center is that if that's my center, that's my first equilibrium point, so I move for a while, it means that I want the second center here in that sector, because then my new rotation will enter, and I don't want it in that part because then I will increase the distance to the initial point. Okay, so I'm only writing this to convince you that I can convert this in conditions, in formulas. So I want, the details are in papers and places, so at the end you have references, but it's something you can do. Okay, so, well, at the end you use all these and you construct the control. So let me show you simulations, and then I'll explain about, well, some comments at the end. Okay, so I will only focus on Geostorm. I've done it for Polar Observer. First I put it in the slides, but then I realized it was too much, and I forgot to erase that sentence there. Okay, so I will only discuss Geostorm. So, well, this is a Monte Carlo simulation. That's a standard. So I start with random initial conditions. I program a simulator, I program a control, and I simply launch to see what happens, okay? So we do it for 30 years and see what happens. Well, that's how it behaves. I'll show plots in a moment because the plots are nice. So it means that no error means that to assume that when I ask the solar sail for an orientation, that's what I get exactly. And that I know exactly where the solar sail is. I mention this because in practice, you don't know exactly where your spacecraft is. You know it approximately. And when you ask for an orientation, you don't get it exactly. You get it approximately. Okay. So on these two things, for a real application, has to be taken into account. I mean, how sensitive is your strategy from the uncertainty in these quantities? So here there are simulations between different errors. So we start increasing the error till the method fails. So it was 2 degrees, 2.2 degrees, which is quite high. But let me show you the dynamics of a sail. So the first 3 plots, this is without errors. Everything is exact. So this is in the synodical coordinates of the resistant free body problem. This is xy, xz, xz. That's what you get. But this is in the saddle center projection. So this starts at that point, and then the control produces. I mean, if you realize of this is, if you remember, that kind of control, yeah. Yeah, those are the 2 centers. So in this center, that's where the trajectory starts. The control, I mean, really reduces it and brings it to the point, but not in this. That one keeps oscillating. Okay. The reason for that is that with a solar sail, you only have 2 parameters of control. I mean, when you do, a maneuver with a rocket, you have 3 directions to do the maneuver. But with a sail, you only have 2 angles to orientate. So when you only have, because you have only 2 angles, you cannot task for many things. So I could bring this center to the origin like this, but then that one would behave not so nice. Okay, but still it keeps the thing bounded. So I mean, we have to do some kind of minimum square problem to try to control everything, but it works. So, and then this is with the errors. I mean, this is very nice and you tend to the point, but when you have errors, that's not so nice because, well, you cannot reach to a point because you are doing little errors in maneuvers. That is also interesting. That's how the solar sail moves. So this is the 2 angles. So there's one angle that really moves between 2 values, while the other really converges to a point. Well, that's how the angles are defined. Okay, so let me do the conclusions. Okay, for instance, understanding the dynamics, and this means understanding dynamics means having the manifolds to explain how the trajectories are nearby, allows you to really control trajectories. That's one of the points. I mean, manifolds are useful for many things, and that's in a space dynamics, that's one of them. I mean, knowing them allows you to take advantage of them, and they are really useful. So we did it for 30 years. I mean, to put a number, it could, I'm sure it runs for longer. Okay, well, these ideas serve for other things. For instance, and it's only one slide, so I didn't want to discuss it. This is a kind of well, we call it surfing, but it's so the idea is the following. This is how to go from one place to another place using a sail and using local invariant manifolds. So imagine we start here in the saddle 1. So this is an equilibrium point that's hyperbolic. So it's a saddle. So you move away. And then the idea is you change your orientation, you displace the point such that, but now you don't want to stay, you want to move away. So you displace the point with the opposite idea such that the point gets there. So you do this. And then you displace the point and you do this. So you can organize a transfer along, a line of fixed points by simply understanding how the manifolds are located. Okay, that's what happens in the centers. So, and finally, I think it's only references there. Yeah. So finally, and this is one of the goals today, is that, I've used linear manifolds to do the things cleanly, nicely, blah, blah. But in fact, if the manifold is linear or not, for all the concepts I've explained, it's irrelevant. I mean, if the manifold is nonlinear, we will talk about nonlinear manifolds, next week. If the manifold is nonlinear, computations will be harder, yeah, but not ideas, not concepts, and not advantages of all this. So, I mean, I've put some reference. I've tried not to put not too many about these things. So it's well, I think that's all, and I think I'm finishing on time. Thank you very much.
Thank you very much. So let's upload. Let's upload. Okay, so we're open to more question.
Yeah, I have a quick question actually about the first method with the rocket. So because I think it's very difficult to be on the stable manifold, right? So what I mean is that you move close to the stable manifold, but then the flow again will eventually bring you away from the stable manifold.
And you keep going, and you keep doing it.
Okay, so you keep doing it until your rocket doesn't work anymore, because that has a
yeah, but that's what happens. I mean, usually to control a rocket near an unstable place, periodic orbit, point, or whatever, you have to do a maneuver every month, every week, depending on the level of instability. And that's because on one side, you cannot land with zero error on the manifold or on the point. That's one thing. And the second is that your model is not exact either.
Mm-hmm.
Your model is not exact.
Yeah.
You could do it for your model. The reality, I mean, you know parameters with 10 digits, not with more. So at the end is a loop. So when you realize you are going away, you compute your maneuver, you do it, until next time.
Okay. So is it convenient to have, this is like a curiosity, but is it convenient to have a smaller maneuver frequently or a larger maneuver once in a while? Like, I mean, I don't know, like maybe, practice what people
Well, it is, the point is that you cannot do maneuver. I didn't mention that, but the point is that you cannot do maneuvers, with short time intervals. Because when you do a maneuver, there's an error in the maneuver. The maneuver is not done exactly. So your rocket, I mean, you ask for 10 seconds of burn, but the push you get, you are not sure. You are almost sure the push you will get, but not sure. And also the orientation. The orientation will also have little errors. So once you do the maneuver, the thing you have to do is to check what has happened.
Okay.
Yeah. So this means to measure again the position of and that takes some time. To measure the position of the spacecraft, that takes some time, and then realize that the maneuver has been perfect, half perfect, and or whatever. And then there's another segment. I mean, so this means it's of course that depends on where the satellite is. It's not the same if this rocket is in the L3 or in L1 or L2 of the Earth Moon, which is close, so we can measure very easily, or it is orbiting Jupiter, between the moons of Jupiter. So I mean, things are more difficult because it's far away.
Okay,
but
thank you.
More question? The students can ask. Don't be shy.
I guess I'll have a question then.
Go.
I would like to know about the solar sails. How, I mean, the influence of the sun and the reflection and the guidance of the sail, how big it is when comparing to the gravitational. I mean, if you're Earth and Sun, you are close to the sun, but if you are Jupiter and Sun, or even further away, like imagine we want to sail until Neptune, how?
Yes. So yes, this is the beta. So let me share again I don't know, when I share, I lose you, so I don't know why this happens. But well,
we are still here, we promise.
Yeah. So let me go.
I think it's the view. You can change your view and you can see us. is depending on the bottom of the view.
On the view.
Yeah, on the upper right, there is view. There is an upper right corner, and you can change the view if sometimes you should. Well, there is a choice. There is a choice if you want to see just yourself or.
Let me go. I'll investigate up to all for this thing. So
Okay.
I'll investigate this. So this is this beta parameter. Okay, the beta parameter measures the push you get from the sail compared with the solar gravitational attraction at 1 astronomical unit from the sun. So this means if you are at the same distance of the sun as the Earth, 1 astronomical unit, and beta were 1, if beta were 1, it means that the push you get from the sail equals the gravity pull you suffer from the sun. So with beta 1, you could stop without orbiting, not falling to the sun, not going away.
I see.
I don't know if that answers your question.
Yes. And then this beta would be like when we're far away, this beta would decrease.
The beta decreases.
Okay.
Not the beta. I mean, let me show you the equations.
Okay.
The beta is always the same value because it's the push you get when you are at 1 astronomical unit.
Okay.
Okay, so then there's this
r distance. Okay.
Yeah,
okay.
so it
Now
goes with the square of the distance.
I see. Okay. Thank you.
Yeah, so that still, I mean, a solar sail is believed to be the most efficient way to send a probe outside the solar system. That's still, I mean, it's and okay, let me a warning. I mean, I've explained how to control with invariant manifolds, yeah, but not everybody is doing this. I mean, there are other methods for doing control and doing. I mean, there's lots of people doing research on optimization, control algorithms. So this is not the only way. Okay, so I'm explaining it as a way of understanding how invariant manifolds and knowing what happens to them is useful to understand what's going on and to derive techniques and do things. That's what I'm doing. And in fact, it's useful. I mean, invariant manifolds have been used in space for missions too, but it's not the only option.
Yes.
Oh.
We stop.
So
I forgot to stop recording, so people are more free to ask questions. So more questions? Yes, because not everyone wants to be recorded.
I mean, if you are afraid if you ask a stupid question, it will be recorded for eternity.
Yes, so there are no stupid questions here, so please feel free to ask. But first, before I want to say it was a beautiful lecture. Thank you. I think we have to. It's a pity that some of the students today, the few students had the classical mechanics test, because I think the people doing mechanics, they should.
Lots of students are doing the test today. This test is classical mechanics.
Yes,
yes. Love this lecture.
Yes. We will. This is good to have recording. On the other hand,
well, in fact, yeah. Now I have it prepared, so I could repeat it. I mean, I'm not offering myself. I mean, for this kind of talk, I mean, the big effort is to prepare it, as you. I mean, all of you know. I mean, the effort is to make decisions, to choose the slides, to prepare the slides. But once it's prepared, I mean, in fact, I'm keeping from myself because I also have to teach courses on time, so I'll recycle it.
Yeah, no, it's very nice, very beautiful.
Yeah, so I said, Tuesday was a very technical, maybe was too tough.
No. Yeah, no, but it was good too. I mean, they're different.
Yeah, today is more geometrical, more simple. And then for the week, I'll use invariant manifolds, not for controlling, but for transport.
That's good.
I have a question, please.
Please go ahead.
Angel, when you change the angles and you change the attitude of the solar sail, your fixed points are no longer of the same type. It's no, you don't have a Hamiltonian system and the stability changes. Okay, what's the consequence of that in the point of view of the
well, two things. I mean, here I have to say two things. One, the solar sail breaks the Hamiltonian character, and that's good, because if energy is preserved, you don't go very far away.
Good.
That's so you see the point, right? So I mean, you really want to break the barriers. If you want to move away, you have to break the restrictions of. So that's something you will take advantage. The second is that this motion of the sail is very small, because you are in a place, you want to control around the place, and you only want to change this point a little, because you are moving a little far away and you want to change it a little. So the eigenvalues move a little when you change the orientation, but you don't have bifurcations. So there's no big changes, because you are in a small region of phase space. That's why you can use linear approximation for the manifolds.
Mm-hmm.
Oh, by the way,
but you don't have no more center saddle. You have spirals, no?
Yes. Yes.
What's
yeah.
the consequence to have spirals? This is the point.
Yeah, it is. That's a good point. I didn't mention, because I was afraid not to have time. So let me get the right slide, and I'll show it to you. That's you are completely right. And in fact, it happens. Oh, sorry. Sorry, I'm looking for here. Let me share. Share. That's the slide. So in principle, with the sail, I mean, the two real eigenvalues, when you put the sail that perturb, they still are real. Mm-hmm. The product or the sum is not longer 0 or 1, or, you know, because you have, but the complex get a small real part.
Mm-hmm.
Yeah?
Yeah.
Okay, so this is small. Okay, this thing is small. So let me explain this properly. So what I do is, first, I ignore it. Okay, I ignore as if it were 0. Mm-hmm. In the same way, I ignore the nonlinear terms in the manifold. So I have an approximation. Yeah, mm-hmm. And I derive the methods. Mm-hmm. So you can complain saying, okay, you are cheating and this will not work because you are forgetting things that could be relevant. But first, it works. And now let me explain you why. So let me go to the simulations. So let's take that one. Okay, for the saddle, no questions, that no problem, but let's talk about the centers. Mm-hmm. Well, so if the centers have a real part, it makes, maybe that's not the best plot, that one. So if the center has a real part, it means that I don't rotate, but I also spiral a bit out, for instance, right? And I'm forgetting that. But when I choose the new center inside here, I'm bending it again back to the point. So in principle, if this amount that you are spiraling out is not very big, and it is not, when you do the maneuver, you put the new center here and you bend the trajectory to the center, you still can do it and it still works.
Okay, I see.
Yeah. Mm-hmm. So yeah, in the same way, I didn't mention that when I do the control, so that's the same thing. When I do this kind of control, I do the maneuver and I bring here. So I will not land exactly on the manifold. I will land nearby. And this accounts for the error in the manifold too. Mm-hmm.
Yeah. Okay.
So it means, I mean, going to the inverted pendulum, if you play, I'm sure you had played, I mean, all of us had played when we were kids to hold an inverted pendulum. You don't need much accuracy to keep it. Mm-hmm. I mean, if we need I don't know, to move our hand with 6 digits accuracy to keep the pendulum up, it won't be possible. Yeah, so it's the same thing. So, I mean, we are used sometimes in thinking in high accuracy, lots of things, and sometimes things can be handled in a much simpler way. So, I mean, knowing where the manifolds are and simply approaching them and doing some maneuvers to cancel the unstable direction, not exactly, but the big part of it, ends up with something that works perfectly because your model, everything already has also errors. It has errors coming from whatever. So it's...
Thank you. Now I see.
More question? The student is silent. The student have question today? Not courageous student. There is one question.
There's a question in the
chat. Yes, Georgia from Greece.
Do your spirals artificial spiral by using the stable manifold on the center? No, I mean, this is, I mean, the point is that our movement of the parameters of the sail only moves a bit, a few degrees. Okay, if you want to imagine, it moves a few degrees because you only want to move the equilibrium point for a small piece. You don't want to send the equilibrium point far away. You want to have it nearby. So, and because of that, I mean, unless, I mean, of course, I mean, unless you choose, you want to stay in a bifurcation point, then if that's where you choose, then you would have this kind of problems. I mean, if you look for an equilibrium point in which you have a bifurcation and you want to stay at the bifurcation, then yeah, I mean, when you move the sail a bit, you can be in one side or the other side, two centers, one center, whatever. But usually that's not the case. So you are in a point which is, let's say, a bit far from a bifurcation. So when you move a bit the parameters, it stays what it was. So it stays center, saddle, center, or whatever. I think that was the question, right? Georgia?
Georgia? Sometimes communication. I think yes. I think it was a question.
Okay.
Yes, thank you.
Okay, very good.
We are warming up. You see, the people are feeling more. It takes some time for the people to get to know each other, and feel free to ask questions. So that's great. So we next lecture will be next Tuesday at the same time, and if you can send us maybe the first lecture or some slides, so people can start studying during the weekend if they want.
Yes, I have to pass you a link because it's too big for mail.
Yes. Or maybe Dropbox.
I'll pass you a link. Yeah, I'll pass you a link.
Yes. Okay, that's great.
Vale.
Okay. Thank you very much once more. And so. And we see you all. Have a great weekend, everyone, and see you all next Tuesday. Thank you.
Thank you. Bye-bye. Bye-bye.
Bye-bye.
Bye-bye, Alessandra.
Thank you. Bye.
Bye, Marisa.
Bye-bye.
Bye-bye. Bye-bye. Thank you. Bye.